So last time around we did lecture 6 on recursion, which is one of the key topics on the course. And as we'll see, it's also the main topic of the second coursework. So what I'm going to do today is slow things down a bit. We've been doing a lot of PowerPoint slides up until this point. So what I'm going to do is the exercises for lecture 6, and I'm going to be doing these entirely on my iPad. And before we start, I found this nice cartoon which I really like, and it's a guy who's learning some programming like you, and he's got some problems with recursion, and he stumbles on this nice sign on a lamppost, and it says, oh, if you've got some problems with recursion, please take one. And of course you can predict what's going to happen. He takes one of the little tickets, and it's got exactly the same thing written on the ticket as well. So this is from Saturday Morning Breakfast Cereals. I really recommend this website if you haven't seen it before. It's worth checking out. So we're going to do the exercises. So we'll start off with exercise 1, which was to define a few simple library functions using explicit recursion. And what we see is that they start off quite simple and they get a little bit more sophisticated and illustrate different things as we go along. So the first one we're going to look at is the logical AND function. And what it's going to do is it takes in a list of Boolean values, and it's going to give back a single Boolean value. So let's have a couple of examples of this first of all, and then we'll figure out how to implement it. So an example would be if we start up GHCI and get the little prompt, and then we said if we AND together a list with all true values, say 3 copies of true, then of course that's going to give back true, because what logical AND does is it takes a list of Booleans and it only gives back true if every one of the Booleans in the list is true. So in this case we've got 3 trues, so we're going to get back true. So another example would be is if we said what's the logical AND of true, and maybe let's put a false in here, and then we have a true, and this would give back false. And it gives back false because we don't have all true values in here. We have a false value sitting in here, so we get back false. So that's what we have to do. How do we actually define this thing? So let's start off with the definition. So what I'm going to do first of all is write down the skeleton for the definition, and I'm going to use the same basic pattern of recursion which we saw a number of times in the last lecture, which as we'll see later on is called primitive recursion. So the idea here is that we're defining the AND function, and we have 2 cases. We decide what we do in the empty list case, and we decide what we do in the non-empty list case. And here I'm matching on a list of Booleans, so I've chosen to call the first Boolean B and the remaining Booleans B's. Okay, so B is the first thing in the list when it's non-empty, and B's is everything else. And then I'm going to use this simple pattern of recursion called primitive recursion, where what you do is you take the first value and then in some way you're going to combine it with the recursively processed remaining values. So we need to figure out what are we going to write here. What are we going to write here in the base case, and what are we going to write between these 2 things here? So we'll do the second one first, because it's a bit more obvious what to do. All we're going to do in the middle here is just simply write logical AND. Okay, and why is this the right thing to do? Well, B here is a single Boolean value, and when we AND together everything in the remaining list, that's the tail of the list, that's going to give us back a Boolean value as well, because we see that we have the bool return type here. So then we have 2 Boolean values, and how do we combine them in the appropriate way? Well, we just use the AND operator, which takes 2 logical values. So that was very straightforward. What do we write in the base case now? Well, what do we fill in here? Well, there's only 2 possibilities because we need to return a Boolean. So we either return false or true, and the answer is true. And why is true the answer? And true is the right answer here because it's the identity or unit for logical AND. So if you logically AND anything with true, then you just get whatever you had. It doesn't change the value of it. So that's the right thing to do in the base case. Often the base cases are units or identities for operators which you're using in the recursive case. So that's the logical AND function. Let's move on to the next example now. So the next example was concatenation. So what concat does is it takes in a list of lists, so a nested list, and it's a polymorphic function. It works with lists of anything, and it's going to give you back a single list. And it does exactly what you'd expect. I think we've seen this a couple of times already now. What concat does is you give it, so I'm going to give it 3 lists of numbers here, or a list of integers, so 1, 2, 3, 4, and 5, 6. And it will just concatenate all of them together, and I'll get 1, 2, 3, 4, 5, 6. So nice and easy. So we saw how to define this using list comprehensions in lecture 5. Let's now see how to define this using recursion. So let's write down a skeleton again, and we're going to be using primitive recursion once again. So we'll follow the simple pattern. And note in particular what I've called the parameters in the non-empty list case. We have a list of lists coming in. So x's here is actually going to be a list. That would be, for example, 1, 2 here. And then x with 2 s's on it, that would be all the remaining lists here. So x with 2 s's is a list of lists. And what are we going to do? Well, we're going to use the pattern of primitive recursion again. So what we're going to do is take the first thing in the list, which is an entire list here, and then we're going to combine it in some way with the recursively processed remaining lists. So again, we can think what's going on here with the types. This is a list of A's. This is also a list of A's, because when we process a list using concat, we get back a list of A's. So we've got 2 lists of A's. How do we combine them into a single list of A's? Well, of course, we just use our old friend double plus. So that's the appropriate operator to put in there. And then it's kind of very obvious what to write in the base case here. If you give me no lists, there's nothing to do, so I'm simply going to give you back the empty list. And notice again, the empty list is the identity or unit for the operator here. If you append the empty list on either side of any other list, it doesn't change that list. It just gives you back what you already had. Okay, so again, a nice, simple definition. So let's move on to a couple of examples where you maybe need to think a little bit more. They're perhaps a little bit more tricky. So the first one we're going to think about is called replicate. This is a really useful library function. So what replicate does is you give it a number, and you give it a thing. It's a polymorphic function, and it's going to build you a list of that many copies of the thing. Okay, so it's a curried function. It's taking an integer, then separately a thing of type A, and then it's giving you back a list of things of type A. So again, let's have a simple example of what this thing is actually going to do. So if we asked to replicate 3 times the character B, what we're going to get back is a list with 3 B's in it. Very straightforward. This is a really useful function for building lists that have multiple copies of the same thing. So how do we proceed this time? Well, this time we have an integer as the argument here. So we're going to do recursion on that. We can't do recursion on the A argument because we don't know what it is. It could be anything at all. So we're going to have to do recursion on the integer argument. And remember, the standard patterns for integers are 0 and n. Just like with lists, the standard patterns are the empty list and non-empty lists. Doesn't always work. It's not always the right thing to do. With numbers, the standard patterns you try first are 0 and n. So let's have a look at the skeleton then. So we're going to say replicate 0 times of some value is something. And then we're going to say replicate n times of some value x is something else. So this time we'll have a look at the base case first. So if I want to replicate something 0 times, that's very easy to decide what to do. There's nothing to do, so I'll just give back 0 copies of the thing. I'll simply give back the empty list. And then you can think, well, what do you do in the recursive case? For example, if I want to replicate something 3 times, what do I do? Well, let's look back to my example here. Oops, let's move my example up here. If I want to replicate B 3 times, what I can do is emit a single B and then replicate it twice. Okay, so this gives me the key to a recursive decomposition of this process. If I want to replicate something n times, I emit 1 copy and then replicate it n minus 1 times. So that's exactly what I'm going to write down now. I emit a single copy of x, and then I'm going to cons it onto replicate n minus 1 of x. So again, for example, if I wanted to replicate 3 b's, what I'd be doing here is this would be 3, this would be the b, I would emit a single b, so that would produce that bit, and then I'd replicate the b 2 times, so that would give me this bit here. So again, a nice simple 2-line definition, but maybe you need to think a little bit more carefully about how this one is actually working. And just as a little additional comment here, if you look in the first equation here, I do not actually use the x on the right-hand side of the equation. I just simply return the empty list. So I could make this one a bit cleaner. I could get rid of the x, so that disappears, and I put the wildcard pattern in here. And if you look in the standard library, this is probably exactly how replicate is defined. So let's look at a last example of a simple function on lists. And this one illustrates a different point. So we're going to look at the indexing function. It's an infix operator. It's the bang bang operator. And it has type, takes a list of a things, and it takes an index into the list, which is an integer. And then it's going to give you back the particular element at that index. So a simple example of this one would be if I take the list A, B, and C, and I index into it at position 1, well, remember, you start counting from 0 when you index into lists in Haskell. So this is the thing at position 0, that's the thing at position 1, and that's the thing at position 2. So if we're indexing in at position 1, we're going to return the B. Okay, very straightforward, very useful function. So now we can ask ourselves, we've got 2 parameters here. It's a curried polymorphic function. It takes a list of A and then an integer and then gives you back a single A. So we could ask ourselves here, which of the 2 parameters are we going to do recursion on? Because the first one is a list, so we could decompose that, or we could decompose the integer argument. And actually this is an interesting example because in this case the right thing to do recursion on is both of the arguments simultaneously. So let's see how this works out in practice. So we're going to have 2 cases for this, and I'll comment on these cases in a minute. So we're going to have, if you're indexing in to a non-empty list at position 0, you will give back something. So I'm just writing down the skeleton for this case. And then the other case is if you're indexing into a non-empty list at position n, so that could be like 3 or 4 or something like that, then that's what you do. So let's look at the 2 cases one by one. So in the first case, we have a non-empty list where x is the first thing and x is everything else, and we want to select the thing at position 0. And remember, the thing at position 0, if I look at my example list, that's the thing at position 0, so it's the first thing in the list, so we're simply going to return x in this case. Okay, so this is a base case for the definition. There is no recursion involved. In the recursive case, we're indexing into a non-empty list at a positive position. So we know it's not 0 because that would be checked by the first case. So for example, if we're indexing into this example list up here at position 1, how could we decompose the problem? Well, what we could do is forget about the first element because we know we're not looking for the thing at position 0 and just look at the remaining elements, which is the list x's. And then if we indexed into that at position 0 rather than 1, that would give us the right value back. So this gives us the key to figuring out how to index in at a non-zero positive position. All we're going to do is, in the recursive case, we're going to index into the remaining list at position n minus 1. So for example, if we're indexing into this list here at position 1, what we would be doing then over on this side here is we would be indexing into the remaining list, and then rather than position 1, we'd be indexing at position 0. Okay, so we have a nice, simple 2-line recursive definition for this function. So there's a couple of points to note about this one. First of all, note that there's no empty list case. Both of the cases work on non-empty lists. So in fact, this function will crash if you give it an empty list, because we don't actually know. If you're trying to index into a list with nothing in it, then what do you do? I mean, you could print an error message, but the Haskell designers have decided just to crash at that point or raise an exception. Secondly, not all of the variables are used in the two equations. So if you look at the first equation, this one here, and we look at the variable x's, it is not used over on the right hand side. We only use x, so we could get rid of that. So I can eliminate that, and I can put a little underscore in here. And if I look at the second equation, over here, the variable x appears on the left-hand side, but it does not appear on the right-hand side. So again, I could eliminate the variable x, make it a bit cleaner, get rid of that, and have a wildcard pattern in here. So I think maybe there's one more exercise. I'll leave this one for you to try yourself. But a point which I'd like to make at this point is that these are very common exam questions. I mean, defining very simple library functions using recursion in various different ways are very common questions that you might find in the exam. So make sure you get comfortable with doing these kind of things. And the kind of thing you might want to do is look at the standard prelude, which I've given you on the web page. Look at some of the library functions, put them away, and then think, can I redefine them for myself using recursion? So before we move on to exercises 2 and 3, what I want to do quickly is an extra exercise. So later we're going to be looking at merge sort, and what I want to show you first of all is how you can implement what's called insertion sort in Haskell. So the first step to this is that we're going to define a little helper function which inserts a number into the correct position in a sorted list. So let's write down the type for this function first. So insert is going to take an integer and a list of integers, which is already sorted, and it's going to put that number into the correct position in that sorted list. So what do I mean by this? So again, let me give you a simple example of this. So if I wanted to start up GHCI and I insert the number 3, and what I'm going to have is a sorted list here. Let's assume I've got 1, 2, 4, and 5. So this list here is already in the correct order, and I want to put the 3 into it. Then obviously what I want to get back is the same list, but with 3 put into the correct position. Okay, so very nice, simple idea. We're taking a single number and then a list of numbers which is already sorted, and we're going to put that number into the correct position. So now we need to think about how can we implement this algorithmically in Haskell. So let's think how we can do this. So the way I'm going to explain this is by kind of imagining we've got a little pointer, or we're kind of sticking our fingers on certain numbers. So what we're going to do is have two numbers that we're paying attention to. So here is the first number. That's the number which we're trying to insert into the list. And then what we're going to do is we're going to start with another little pointer or another little marker saying that's where we're starting off. And all we're going to do is we're going to copy values from this list here until we find one which is bigger than the value we're trying to insert. And that tells us we've then found the right position to insert. So let me explain what that actually means in practice. So let's do this. So what are we going to do? So we're paying attention to the number 3 and the number 1. And then we say, which one of these two numbers is smaller? Well, obviously it's the number 1. So what I'm going to do is, let me get rid of this. I'm going to copy down the number 1 because that's the smaller one, and then I'm going to advance the little marker. So I can select that one here and advance it. Okay, and then I'm going to do exactly the same thing again. I'm going to compare these two numbers. I'm going to say which is smaller, the 3 or the 2? Well, obviously the 2 is smaller, so I'm going to copy that one down. So the 2 will get copied down, and then again I'm going to advance my little marker to the next point in the list. And again, same game, say which is smaller, the 3 or the 4? Well, we see now that the 4 is bigger than the 3. So what we have found now is the correct position to output the 3 in the list. So we can put the 3 here. And then all we're going to do then is we've already found the correct position for the 3. We know everything in the remaining list is at least as big as 4, because remember it's a sorted list. So we can simply copy down these elements. So I can copy down the 4, move my little marker on, and then I can copy down the 5, and then I am done. Okay, so this is the idea. We're starting at the beginning of the list. We copy values from the list until we find one which is larger than the new value. And that tells us we found the place to insert the new value. We insert it, and then we just copy everything else from the list. Okay, so the idea now is how can we actually implement this procedure in Haskell. So let's have a think about this. So we're going to define the skeleton for the function as usual first. We're going to say, how do you insert the value x into a non-empty list? So that's going to be a base case. And then how do you insert the value x into a list y colon y's? Okay, let me make a little bit more space here. So these are our two skeletons. So let's look at the base case first of all. What does it mean to insert a value x into a list which has got nothing in it? Well, this is an easy one. You just put the value into the list. So I just put the value x straight into the list here, and I'm done. Then we can think about the recursive case, and we can ask ourselves, well, how do we proceed? Well, it depends on which of the values is smallest. Okay, so the way that we're working here is, this is like my first pointer. That's the first pointer we had on the previous slide, and this is where I'm currently sitting. Okay, so I need to check which of these two values is actually smaller. Okay, so I'm going to have a conditional in here. I'm going to say if x is less than or equal to y, then do something, else do something else. Okay, so now we need to think, well, what's the right thing to do? So if x is smaller than or equal to y, that means we've already found the right place to output x. Because if this is smaller than that, we know it's also smaller than everything in the remainder of the list because it's a sorted list. So in this case, all we need to do is output all of these three components and we're done. Okay, so this is a very easy case. If x is less than or equal to y, we're simply going to output x because we found the right place to put it, and then we'll just copy the remaining stuff over. So very nice, easy case. The other case is when x is bigger than y. Okay, so in this case, x is bigger than y. So what are we going to do? Well, y is smaller, so we will output that. So we'll output y. And then what we want to do is advance our pointer and then continue. Okay, so if our pointer was sitting here, we want to advance it into the first element in the remaining list. So what does this actually mean in practice? Well, it means we will output y and then we'll continue, oops, wrong color. We will continue by inserting the value x into the remaining list. Okay, so this is the recursive case. So let me just explain it one more time. So if we find that x is bigger than y, then we will output y because it's a smaller value, and then we'll just continue to try and insert x into the right place in the remaining list. Okay, so this is a more sophisticated function than we've seen up till now. It's a really good exercise for yourself to try and write it. So look at an example like this, kind of track things through with your fingers or something like that, and then try and write this definition for yourself and actually type it into GHC and check that it actually works. So what we're going to do now, just to wrap this extra example up, is I'm going to show you how to implement something called insertion sort. Insertion sort. And I can explain insertion sort very simply in words, and then I'll explain how to implement it in Haskell. So in words, there's two cases. So the first case is that if I give you a list with nothing in it, it's already sorted. And that's going to end up being a base case for our definition. And then non-empty lists are sorted by simply inserting the first value in the list into the result of sorting the remaining values recursively. Okay, so that all sounds a bit of a mouthful, but actually when you implement it in Haskell, it turns out to be extremely straightforward, and it's just a two-line definition. So let me show you how to do this. So I'm going to define isort, and I'll just say for simplicity here that it takes a list of numbers, but we could generalize this and make it sort anything which has an ordering on it, which you might like to try playing around with for yourself. But here we're just taking a list of integers and giving back a list of integers, and isort of the empty list is something, an insertion sort of a non-empty list, x followed by x's, is going to be something else. Well, when I explained it in English, I said the empty list is already sorted, so there is nothing to do. And then I said non-empty lists are sorted by inserting the first value x into the result of sorting the remaining values. So you could write isort of x's. Okay, so it's a very simple recursive decomposition. Empty lists are already sorted, nothing to do. For a non-empty list, we recursively sort everything else. That will give us a sorted list, and then we put the first thing into the correct position. Okay, so if you've seen insertion sort before, you might want to think, how does this definition in Haskell compare to what you've seen in other languages? And I hope you'll see that it's much, much clearer and much, much shorter as well. Okay, so to wrap things up today, we're going to do the merge sort example, which is exercise 2 and 3. And first of all, we're going to define a simple helper function which merges together two sorted lists. So we're defining a helper function called merge, and it takes a list of integers which is already sorted and another list of integers which is already sorted, and then it's going to give back a final list of integers which is sorted. And the idea is it simply merges these two lists together. So we could have a simple example of this. Let me just move this down so I've got a bit more space. So if I'm merging, here's one sorted list, 2, 5, 6. They're in the correct order. Here's another sorted list, 1, 3, 4. These are in the correct order, and we're going to get back a single sorted list, 1, 2, 3, 4, 5, 6. So then again, we can think, what's a kind of algorithmic procedure for achieving this behavior? How do I take this sorted list and end up with this single sorted list down here? Well, again, we can think about this in terms of having little markers. So let's have two little markers. We're going to have both of them sitting at the start of the two lists. And then the procedure this time is even simpler than the last one. All we're going to do is copy the smaller value until one of the lists runs out, and then we can copy the rest of the other list. So what does this mean in practice? So let's look at the example. So here, I'm first of all pointing at 2 and 1. So the 1 is smaller. So what I can do is output the 1. So I output the 1, and then I just advance my little pointer. So that goes to 3. And then I think, which is smaller? Is it the 2 or the 3? And of course the 2 is smaller, so I can output the 2. And then I advance my little pointer up to here. And let's see what we've got now. So we've got a 3 and a 5, so we'll output the 3. And this pointer will advance to there. And now we think we've got a 4 and a 5, so I can output the 4. So the 4 comes out. And now I've exhausted the second list, and you can think about this pointer moving to the end now, or just moving off the end. So I've got no more numbers left in that list. So the only sensible thing to do at this point is simply to copy over all the values in the other list. So I could just copy over all the other values, because I need to merge these in as well. So I can copy over the 5 and the 6. So this is the idea about how you can implement this kind of algorithmically. You're always just looking at the next numbers, comparing them, outputting the smaller one, until one of the lists is finished, you've got no more elements, and then you just copy over all the remaining elements from the other list. So let's implement this one using a recursive definition. So let me give you the skeleton as usual. So I'm going to merge the empty list with something. And I'm going to merge something with the empty list, because either of the two lists could be empty. So this is the case when the first list is empty. This is the case when the second list has been exhausted. And then the recursive case is we're going to match on the two lists. So we have x colon x's, y colon y's, and we know they're both non-empty because the empty list cases have been trapped by the first two equations. And then we need to figure out what to do. So let's look at the base cases first of all. This one, first of all. If the first list is already exhausted, I just need to copy over the remaining list. So I just need to copy over y's. And then it's the same here as well. In the second case, if the second list has been exhausted, then I still need to copy across everything in the first list. So I can just have x's here. And then about the recursive case, and I need to think, what do I do? So again, you think about your little pointers. So if I go to red and say, this is my little pointer here. This is the first thing in this list, which I haven't yet looked at. Then we have the first thing in the other list. And we just compare the two values and we see which is smaller, and then we will decide what to do. So very straightforward. So I can say, if x is less than or equal to y, then do one thing, else do another thing. Okay, so let's think about the first case then. So if this thing is smaller than that thing, so the x is smaller than the y, what I'm going to do is simply output the x, because I know that's the smallest thing, and then I just need to continue merging with everything else. And what's the everything else? Well, I haven't looked at x's yet, and I haven't looked at y colon y's. So the recursive case then is everything which we have not yet considered. So we'll continue by merging the rest of the first list, so that's x's, and then the whole of the second list, because we haven't output anything from that yet. So that's the first case. The second case is exactly the opposite. So if we're looking at the two values and y happens to be the smaller one, then what we're going to do simply is we'll output y, and then we'll continue merging with everything that we haven't looked at yet. So we haven't looked at x colon x's, and then we haven't looked at the rest of the stuff in y's. So again, nice simple 3-line recursive definition. I strongly suggest that you have a go at this yourself. Make sure you understand what the function's doing, kind of track through an example with your fingers or on a piece of paper, and then try and implement it in Haskell like this. It's a really good exercise on recursion. So the last thing now we're going to do today is exercise 3, which is to implement what's known as merge sort, which again, some of you may have come across before. So again, I can explain it in English first of all, and then we'll implement it in Haskell. And what we'll see again is that the Haskell definition basically is just typing in the English description. It's very, very straightforward. So the two cases this time around are lists of length less than or equal to 1 are already sorted. So if you have the empty list or you have a singleton list with one thing in it, that's already sorted. There's nothing to do. And then the other case is other lists can be sorted by splitting the list into two halves and then sorting those and then merging the results. And what I mean by splitting into two halves, well, approximately halves. I mean, if you have a list of 10 things, you could split it into two lists of 5. If you had a list of 9 things, you could split it into a list of 4 and a list of 5. So approximately into half. So how do I implement this in Haskell? So let's define, msort. Defining msort for merge sort. Again, I'll just give it a simple type, a list of integers to a list of integers, but this could be more general. We could sort anything which has an ordering on it. And I've got 2 base cases. So in English, I said, if you have lists of length less than or equal to 1, these are already sorted. So I can fill in the 2 base cases straight away. If I've got the empty list, there's nothing to do. I get the empty list. And if I've got a non-empty list or a list with one thing in it, a singleton list, I just return exactly the same thing. So then the recursive case says, if you've got any other list, x's, so we know that it's got at least 2 things in it, because this traps the case when there's 0 things, this traps the case where there's 1 things, and lists always have at least 0 things in them, so this is the case when you have 2 or more elements. So how do you sort a list with 2 or more elements? Well, all you're going to do is you're going to sort the 2, well actually let's do it back to front. I'm going to have a little where down here. What we're going to do is split the list into 2 parts. So we're going to split it into a list y's and a list z's, which is given by halving the list x's. So I'm going to leave this one as a little exercise for you to define. How do you split a list into 2 halves? And I'll give you a hint. One easy way to do it is to simply use take and drop. Maybe take the length of the list, divide it by 2, and then use that number to take and drop elements from the list. But I'll leave you to actually type in the Haskell for that for yourself. So a little exercise. So I'm splitting the input list x's into 2 halves. Y's will be the first half, z's will be the second half. What do? Well, all I'm going to do is I'm going to merge sort recursively the first half, and I'm going to merge sort recursively the second half, z's. So what I'm going to have here now is 2 sorted lists. But what I want is a whole sorted list. So what do? Well, I just use the function we've just defined. Merge takes two sorted lists and gives you back a single sorted list. So all I need to do here to finish this off is simply to write merge in here. And again, this is very easy. This is basically just typing in the English definition of what merge sort is, and you get a very, very simple 3-line definition. So again, you might like to compare this to implementations of merge sort, which you have seen in other languages. So that's it for today's exercise class. I will see you again next time.